1 month flight to its destination, and 5 months of calibration. On December 25, 2021, NASA launched the most advanced telescope ever built, James Webb Space Telescope. The telescope deploys as it travels to its destination of Lagrange L2 point, 1.5 million kilometers away from Earth. But before taking the first pictures, Webb telescope needs to cool down to operating temperatures and calibrate all of its scientific instruments, an extremely delicate and time-consuming process that can take months to complete. Actually, the first data was successfully received a little more than 2 minutes after launch. Right after powering the high-gain antenna, Webb started transmitting telemetry data. Webb begins to cool down during the deployment process itself. Following the sunshield deployment, the mirrors and instruments quickly start to cool in the shade of the sunshield. After Webb achieves its L2 orbit, the observatory takes about a week to cool down to a point where its near-infrared camera, an IR cam, can start operating to support telescope alignment. An IR cam will detect light from the earliest stars and galaxies in the process of formation, the population of stars in nearby galaxies, as well as young stars in the Milky Way and Kuiper Belt objects. So it takes roughly 3 additional weeks to get the shaded portion of the observatory down to its extremely cold operating temperatures of less than 40 Kelvin. Because Webb mid-infrared instrument MIRI has extremely sensitive detectors, which allow us to see the redshifted light of distant galaxies, newly forming stars, and faintly visible comets, the instrument uses a cryocooler to reach its significantly lower operating temperatures of 7 Kelvin. It independently takes much longer to achieve its full cooldown, just under 100 days after launch. Because of the unique circumstances of the stable space environment, the Wavefront sensing system architecture on James Webb is different from large active telescopes on the ground. Most significantly, James Webb is free from atmospheric disturbances and gravity-induced deformations, which are dominant factors requiring rapid correction for active and adaptive telescopes on Earth. Instead, James Webb only needs correction for wavefront aberrations that change much more slowly than the durations of typical science observations. In particular, the need for wavefront corrections during science operations will be mostly due to temperature changes that cause slight thermal expansion and contraction of portions of the observatory, typically on timescales of several days. This allows the use of the science instrument imaging detectors for periodic measurements, rather than requiring dedicated wavefront sensor detectors or continuously active segment edge sensors. Once the Webb is significantly cool, its NIR cam instrument, or the primary wavefront sensor, which contains several components in its pupil wheels, is able to help determine that light is correctly following its path through the mirrors and instruments. So the next is the process of adjusting each of the individual primary mirror segments using actuators or tiny mechanical motors. Each primary mirror segment has actuators on its back that provide 6 degrees of freedom, as well as control over the radius and curvature. The secondary mirror is also controlled in its 6 degrees of freedom. Thus, there are a total of 132 degrees of freedom in the telescope that needs alignment, plus the focus mechanisms in each of the science instruments, apart from MIRI. Other alignments such as the tertiary and fine steering mirror have been established during observatory assembly on the ground and are significantly rigid not to need correction after launch. The adjusting process is called wavefront sensing and control. The NIR cam instrument measures any imperfections in the alignment of the mirror segments that prevent them from working as a single mirror. Once in space, each of the 18 mirror segments must be aligned to within a fraction of a wavelength of near-infrared light, mere nanometers, or about 10,000 times thinner than a human hair. The adjusting process will intersperse individual wavefront sensing and control tasks, initial activation and checkouts of the science instruments, and observatory-level calibration tasks that involve many subsystems across the whole observatory, such as the Goddard and attitude control system. The process, expected to take several months, comprises a large portion of the 6-month-long commissioning phase. Because an IR cam is the main wavefront sensing sensor, high-quality images will be first achieved on an IR cam prior to any other instruments, about halfway through telescope commissioning. The multi-instrument sensing process then adjusts secondary mirror alignment to optimize image quality over the full instrument suite. Shortly after the telescope is fully aligned, a stability characterization assessment will characterize the observatory response to changes in the spacecraft attitude with respect to the Sun. This will begin quantifying stability in flight and will better inform subsequent wavefront maintenance. In the final months of commissioning, Webb points at a variety of representative science targets to test and characterize all of the instrument capabilities. Data is collected using each observing mode of each instrument and then run through data reduction pipelines to ensure accuracy and precision. Further calibration programs happen during the first year of science to understand the limits and sensitivities of the various modes and capabilities. Routine science operations begin after 6 months of commissioning, when all mirrors have been aligned and all instruments have been calibrated. During this time, the wavefront will be monitored periodically and alignment corrections made as needed. Nominally, the wavefront will be measured every 2 days using NIR cam weak lenses. Corrections are expected to be relatively infrequent, no more than every 2 weeks, and perhaps only a handful of time per year. The sensing and control processes together will take about 1 or 2% of observatory time, which is accounted for as part of the observatory calibration overhead.